Hey everyone, welcome to this explainer on programming the physical web. I'm absolutely thrilled you're here today because we're going to explore a truly fascinating intersection. We're looking at exactly how traditional software development is evolving to literally control the physical world around us. We're going to unpack the architecture, the really strict hardware constraints, and the networking protocols that make the Internet of Things, or IoT, actually tick.
So let's just dive right in. How do software developers actually bridge that massive gap between traditional digital code, the kind running your web browser right now, and physical objects? Things like a smart thermostat, maybe a soil moisture sensor, or even a giant industrial actuator. Well, it's not as simple as just uploading a Python script to a cloud server. We're dealing with a messy, real-world environment here, and that requires a fundamental shift in how we think about programming.
As author Andy King hits the nail on the head in his book, Programming the Internet of Things, he says, the IoT pushes practitioners outside of their comfort zones, starting with bare metal code on constrained devices. And he's so right. Unlike building a slick mobile app where you've got gigabytes of RAM and these massive batteries, IoT development forces you to write code for severe hardware limitations. I mean, we're talking about devices with less memory than a single low-res JPEG image. You literally have to care about every single kilobyte of memory and every milliamp of battery life. It's just a completely different ballgame.
All right, so here's our roadmap for today. We'll be covering 1. The IoT paradigm shift, 2. Cloud tier versus edge tier, 3. The reality of constrained devices, 4. Where software meets hardware, and finally, 5. Communicating with MQTT.
Okay, starting us off with Section 1, the IoT paradigm shift.
Moving right along to Section 2, Cloud tier versus edge tier. Now looking at this macro-level architecture, notice how clearly it defines the boundaries. Right up at the top in the cloud tier, that's where you handle infinite scale. It's where your heavy data processing, your long-term storage, and your complex analytics happen. But look down at the bottom, the edge tier. This is where the messy, heterogeneous physical world actually exists. This is exactly where your sensors and actuators live, collecting raw telemetry and interacting with the environment on local networks, way before anything ever reaches the public internet.
Let's zoom in a bit for Section 3, the reality of constrained devices.
Okay, so once you're down in that edge tier, the rules of software development completely flip. The crucial thing to understand here is the stark contrast between the two main types of devices living at the edge. On one side, you've got your gateway devices. These are pretty powerful, they often plug directly into a wall for power, and they act as local aggregators that can route data straight to the internet. But on the flip side, we have constrained devices. Think about a sensor running on a single battery for 5 years in the middle of a remote farm field. They have incredibly strict processing and power limits. They rely heavily on deep sleep cycles just to survive. That means you can't just casually send massive, heavy JSON payloads over the network. You've got to optimize every single byte. Plus, these constrained devices generally don't support direct packet routing to the public internet at all. They absolutely depend on that gateway to communicate with the outside world.
This brings us to Section 4, where software meets hardware.
So how on earth does a line of code actually interact with the physical environment? Well, it all begins with sensing. Unlike a web app that just sits there and waits for a user to click a button, an IoT device runs an infinite loop, a constant setup and loop paradigm, meaning it's constantly polling its environment. A hardware component interprets a mechanical input like a change in ambient temperature or humidity and converts that physical change into electrical voltage. That voltage is then translated into the digital ones and zeros that your code can actually process. Pretty cool, right?
And right alongside sensing, we have actuation. Actuation is basically the exact reverse process. It's when your code makes a decision, say it recognizes that a temperature threshold has been crossed, and it triggers an electrical signal to create a mechanical output. This could be sending voltage down a GPIO pin to physically flip on an HVAC system, or maybe close a water valve. It is the literal bridge between the digital and the physical.
But here's the real challenge. Testing actual physical hardware during software development can be incredibly tedious. I mean, you can't exactly manipulate a room's actual temperature up and down all day just to test your thermostat code. So IoT developers rely heavily on simulation. You might use a software generator class to simulate raw data, test your thresholds, and just log the actuation triggers locally to make sure your logic is sound. And to take it a step further, developers often use hardware emulators, like a virtual Raspberry Pi Sense hat. This lets you safely test these sensing and actuation interactions visually, long before you ever deploy your code to a real physical board.
All right, let's talk networking in Section 5, communicating with MQTT.
Okay, so once your constrained device has successfully read the physical world, it obviously needs to share that data. But how do these highly constrained, sleepy little devices manage to reliably share their telemetry back upstream to the gateway without completely draining their batteries? Well, let's look at a bit of a protocol showdown. If you're a traditional web developer, you're probably super familiar with the request/response model. Think HTTP. It's a one-to-one client-server relationship. It's reliable, sure, but it is incredibly heavy and requires a ton of overhead. For the Internet of Things, we instead use the publish/subscribe model. This is a one-to-many approach that relies on a central broker. It's incredibly lightweight and absolutely perfect for constrained devices running on unstable networks. To put it in perspective, if you're building a smart agriculture sensor 5 miles out in a field, you'd probably use LoRaWAN. But if you're building a smart home device, you'll use Wi-Fi and a protocol like MQTT, which is, without a doubt, the undisputed industry standard for this.
Now, notice how this MQTT architecture actually works in practice. The publisher, say our sleepy little temperature sensor, never talks directly to the subscriber, which might be our gateway device. Nope. Instead, the publisher establishes a connection and routes its data payload through a central MQTT broker. The publisher and the subscriber are completely decoupled from one another.
So the way they actually find each other is through something called topics. Here is how the life cycle flows. Step 1. The publisher sends a message tagged with a very specific topic name. And heads up, topics are case-sensitive and hierarchical, looking something like building 1/floor 2/temperature. Step 2. The broker receives this message and filters it based on that topic. And finally, step 3. Any subscriber that has previously told the broker, hey, I want to hear about building 1 temperatures, instantly receives the message. It's a brilliant way to ensure the right data gets to the exact right place as efficiently as possible. And under the hood, MQTT maintains this extreme efficiency using tiny little control packets. For instance, when a client wakes up, it just sends a super lightweight connect packet to the server, and the server replies with a CONAC, or connection acknowledgement. These packets are specifically designed to have minimal byte overhead. That means your device spends way less time transmitting data over the radio, which directly translates to saving precious battery life. But a crucial warning here. You absolutely must design for security from day one. Even though these packets are tiny, transport-level security like TLS is totally mandatory. You never ever want to be sending your data in plain text across a network, no matter how trivial you think the sensor reading is.
All right, we've covered the macro architecture all the way down to those lightweight protocols. But ultimately, mastering the Internet of Things comes down to a fundamental mindset shift. If every single kilobyte of memory and every milliamp of power truly matters out there at the edge, how are you going to redesign your code to survive the physical world? It's a really fascinating challenge to tackle for your next project. Thank you so much for joining me for this explainer, and I genuinely hope this helps you go build something incredible out there at the edge.